Hello, my name is Baron Hoffman. I'm a senior in the Biosystems Engineering program at the University of Kentucky, and my final project will be a general informational report on the future solutions to heat dissipation and problems in electronics. And this is my progress report. So this is going to be the organization of my presentation. I'm going to start off with the purpose, then move to the intended audience, and then an introduction to what the substance of my report will actually be about, like the background, what I found so far, and then what I still need to do. So the purpose of this report is, like I said, a general informational report to study the future solutions to heat dissipation in electronics as our society becomes increasingly reliant on electronics. This is a very pressing issue, and we need to find more efficient, effective solutions. Intended audience are electrical engineers or electronic developing companies such as the ones shown, Apple, Amazon, Microsoft, which are three of the biggest technological leaders in our society right now. This will be very beneficial to them. I'm sure they have many engineers trying to solve these problems that I'm reporting on. So background, huge problem with heat and electronics. The biggest problem is thermal management. As you all may know, printed circuit boards have many components, whether they be LEDs, resistors, transistors, bunch of electrical components that generate heat in a circuit. And the accumulation of this heat leads to many problems in the actual system. It can lead to system failure from water generated from condensation. And it's becoming more true as our world is transitioning to smaller technology like thinner phones, thinner TVs, handheld devices, controllers, all over the place. So historically, we have these big old dinosaurs and the big TVs that you can think of, like these big monitors. They used to have fans built into their printed circuit boards, if you can see down here, to cool off the components. The problem is these take up a lot of space and they are very unreliable because the fan is one of the leading sources of system failure since it consists of moving parts. It's very unreliable. And unreliable parts lead to decrease in productivity, and this can lead to very big commercial industrial issues. So the present solution now, the start of about the 2000s, we introduced passive cooling, which consists of multiple components you can see here, like heat sinks, thermal interface material, heat pipes, thermoelectric modules, thermal grease adhesives. But the biggest contributor to this passive cooling will be heat sinks. Basically consists of a metal material, usually consisting of fins, which basically throughout their surface area dissipate the heat through conduction, direct contact with other electrical components. It's better than fans because it's more reliable. It doesn't depend on moving mechanical parts. It's also cheaper and more compact, like I just mentioned, for our increasingly small, thin electronic world. So as you can see in these diagrams right here, this is a printed circuit board without any heat dissipation devices, so you can just see the chips. So this elongated elevated surface is a heat sink where heat will dissipate, and then over here is the heat pipe and some silicone thermal pads. So basically in the following figures, figure 2 is a temperature distribution, so you can see without any heat dissipation devices, those boards are going to be very hot, as you can see by the red. Once we add heat sinks, they become less hot. And then the other components with the heating pipe and the thermal pads, they cause for more temperature distribution and consequently more heat flux, which is the ultimate goal of this. So this is the graphical results of the figures previously shown. So as you add more heat dissipation devices, you're going to have a decrease in temperature on the surface of your boards, which is the goal, and more heat flux. So less temperature, but more heat flux is the goal. You can see these values down here, starting off without a heat sink at 700 Kelvin, and then with all components down to nearly, more than half, which is very, very beneficial. So as I mentioned, the problem is our world now craves thin, small. Small is the new big, as you may hear. So we don't like these big old heavy, inconvenient monitors or phones. We like thin iPhones, LED TVs, Apple Watches. So, but the problem is we like these. That's an increase in the thermal load, but also a decrease in the actual space that we have to keep that heat in. So it's really a lose-lose, and that's what we need to find better solutions for. So one of the potential solutions that I have been evaluating presently is what's called Versarian copper. So what this does is it maximizes the surface area, which is already the goal of a heat sink in itself, but it creates these microporous structures. So with these structures, it is increasing the surface area and consequently increasing the dissipation through this material. And it uses copper because that is a very big conduction factor for heat. So the thermal transfer will be very large. So what I do still need to do is I need to find some more case studies on this Versarian copper that I just mentioned. I'm still looking for scholarly articles, and I've been in contact with a few professional electrical engineers. And then other advancing heat dissipation techniques. One is called coating, which kind of mimics sweating in mammals. So as humans get hotter, our body through homeostasis starts to sweat, put water on us. And this is a current electrical heat dissipation technique that's being studied right now. Basically takes the heat from the boards and vaporizes it, turns it to water, then vaporizes it. So that's another one that I will be evaluating. And these are my current references, and it's the end of my presentation. Thank you.